Now, our goal is to compute the design effect for the simple random cluster sampling. To do this, we need to introduce a particular parameter, so-called intra-cluster correlation coefficient. It is a measure of homogeneity within clusters. Thus, the word uh, intra means within. We will only consider the case with mi equal to m, the same cluster size. So the intra-cluster correlation coefficient is defined as something like this. So this looks correlation, right? The formula here looks correlation. So correlation for j not equal k. So that means for different element, but within the same cluster, So basically, this is the correlation among different units, different elements within the same clusters. So that how to express it in the population level. Basically, you enumerate all the population and then enumerate all possible covariance and then add up, something like that. So denominator is just the variance. So the summation here, j not equal to k, means that you sum over all element excluding the same one, right? So basically, you have how many of them? So without this, for just jk, you have m squares, right? So you have m square terms inside the summation, but here you have m squared minus m terms. Now, let's express this intracluster correlation coefficient term in terms of the SS within and SS total. Okay. So the idea is in here. Let's write it. Let's write this one. So let's write it. Triple summation, right? So I and j not equal to k, and yij minus y bar u, yik minus y bar u, divided by double summation ij yij minus y bar u square times what ni times m minus 1, and then ni times m. So you basically have this. Okay. So now let's look at this first term. Okay. So how to write it? We can write it. So you can. Let's first take a look at this weird cross product term. So the idea is you can use this algebra. So how you can get this cross product? You basically square this and then subtract the something like this, right? So the summation, and then once you do that, then you apply the summation over I. Okay, and then see how you can write it, and so you can view this as a summation I, and then inside that's basically m times y bar I minus y bar u and squares. Not really, don't have enough space. I should make the oops. Okay. And okay, so let's do this way. So we can write it. I can make the m times y bar iu minus y bar u squares minus the second one is just so this second term is not really difficult. It's just and then this guy is m times, right? M times summation I and then summation j. You can, or you can write it, or you can check that this is actually SS between m times SS between minus this guy is SST. Okay, I think it is too much. So let's write it here. Okay, so my point is that you have something, some kind of some term like, right? And then 1 over m minus 1. And then the numerator here, the first term, is actually m times SSB minus SST. Denominator here is just SST. Okay, so that's it. And now we have only to write it, simplify it. So you can write it SST minus SS within minus SST and then do some algebra. So SST m minus 1 m minus 1 SST cancels, so you end up getting something like okay. So that's this one. Okay, so we just proved this. Okay, and now SS, what is SW? By the way, SW is SS within divided by okay Ni times m minus 1, and SW is SST divided by Ni times m minus 1, but minus 1 you can essentially ignore. So you can roughly say something like this. So you can roughly, okay. So the ratio. So if you compute the ratio, then you have a Ni terms cancels out, so you end up getting this equal to this. Okay. So that proves the first property, and also the SST is SSW plus SSB, and SSB is always positive, not negative. So you end up getting this inequality. So that means you have a the lower bound is 0 and upper bound is SST. So that means if SS within is equal to SST, then you obtain this one. Okay. So that means when SS within is SST, so that means SSB is 0. So that means y bar I is all equal to y bar u. Okay. So that is something like this. So perfect heterogeneity in cluster. So it's basically, if you can just look at one cluster only and it's same as the population. So that's kind of weird situation. What about this? What about the other extreme? The other extreme is that SSW is 0. So what is SSW? SSW is Yij minus Y bar U IU. So that means it's like this. So that means U. So every element in the same cluster are equal, right? So that means perfect homogeneity in cluster. So in practice, uh, clusters are kind of homogeneous. I mean, the element has some sort of homogeneity, a little bit of homogeneity in reality. So we don't have the perfect homogeneity, but usually rho will be mostly positive. The higher, that means the more positive, more homogeneity, something like that. But anyway, the other extreme, SSW is 0, that means rho equal to 1. So now we can use this law to express the variance form. So what we want to do is, this is the main result, right? This is the variance on the cluster sampling. So we want to express SB square in terms of the intra-cluster correlation. So how to do that? We need okay, we can use so okay, so the idea is to use this property, but we want to write it in terms of SB. So SB square. So we want to do some algebra further. Plus m over m minus 1 SSB divided by SST, and then SSB is equal to rho plus 1 over m minus 1 m minus 1 over m times SST. So that means 1 over m minus 1 rho SST divided by m. And so SB square is SSB divided by Ni minus 1. So that means between, and so that means 1 m minus 1 rho times SST divided by n m minus Ni minus 1 equals times S square. Okay. So we have so that basically is this. So we use this, and then variance of the y bar simple random cluster sampling is 1 over n oops, sorry, this is not correct. What am I doing? Okay, and then SB square. So we want to use this property, this equality, to plug in, and then oops, I don't have a space. So then that means we can just use this one instead of this one, right? So that basically gives the gives you what? That it gives you if you use this, then that is the variance on the simple random sampling of y bar times 1, this factor, times 1 plus n minus 1 rho. Okay, so that's exactly this one. Okay, so that means what? That means your design effect is actually variance of your current sampling design, which is the simple random cluster sampling, divided by simple random sampling, the same size. So that you just divide it by here, then you end up getting this term, which is called design, which is design effect. So that is the design effect on the simple random cluster sampling. Okay, so rho is, as I said, rho is usually positive. So design effect is more likely to be greater than 1. So effective sample size is n. N is actually ni times m, right? So the you divide by this something some design. So this is a design effect. So that is the effective sample size. So for example, so rho is positive but usually not really high. So say that rho is 10%. The correlation is 0.1. Within cluster correlation is within, and but you suppose you have 11, then you have a 10 times 0.1, so which is 1, right? So you 1 plus 1, so that is 2. So even though the correlation is weak, m is if m is large, then your design effect can be large. Okay, so design effect 2 means that we need to sample about 2 times n elements in cluster sample to get the same precision as simple random sampling of size n. Okay, so that means if your current sampling current cluster sampling has a sample size 100, then on the simple random sampling it will be same as 50. So that means that is the meaning of the design effect equal to. Okay.